All right, let's jump right into this. Welcome to this explainer, where we're venturing into the glitchy, high stakes, and honestly, pretty wild world of Java memory management. Now, if you've been coding for a while, you probably think you have a solid handle on how objects are created, right? Well, today we're going to look at why your pristine, perfectly compiled Java code might actually be silently spawning dead bodies right under your nose. Consider this your survival guide to Java constructors.
It's a pretty provocative question, isn't it? Why does Java keep spawning dead bodies? We always hear about Java being this incredibly safe, managed environment. There are no manual pointers to mess up. We've got an automatic garbage collector cleaning up our messes. It feels bulletproof. But as you're about to see, that supposedly safe memory allocation hides some seriously dark and highly inefficient secrets. Our goal today is to get you fully equipped to survive this cyberpunk coding landscape. Scene 1. The Born Safe Lie.
Okay, so this perfectly illustrates our first major point. Over in C or C++, you are quite literally in the Wild West of RAM. If you declare an integer named health without actually giving it a value, RAM just hands you whatever random garbage data happens to be sitting at that memory address. So your character spawns in, gets handed a health value of, say, negative 32,768, and just instantly explodes. Good times, see? Now contrast that with Java, which essentially acts as your overprotective nanny. In Java, if you declare a player class with health and alive variables, Java steps right in to protect you from that random memory garbage. Java literally looks at your code and goes, "No, my sweet baby object, you are born safe." So it silently and automatically sets your health integer to 0, your alive boolean to false, and any object names to null. But hold on a second. Take a step back and think about what that actually means for a video game. If your player spawns with 0 health and an alive status of false, didn't Java just automatically spawn a corpse? Brilliant engineering, Java. 10 out of 10. That supposed safety net actually creates a total logical nightmare. Scene 2. Overriding the nanny. So, how do we actually stop our game from being a graveyard right out of the gate? Well, we take back control from Java. We overwrite its flawed default constructor with our own explicit instructions. By adding a custom constructor where we explicitly set this.health to 100, we are flat out telling Java, hey, when a new player object is called into existence, do not use your default 0 value. Set that health to 100 the exact moment of creation. And by doing this, bingo, our player is actually born alive. We've hit the magic number 100. We've successfully conquered memory allocation and revived our digital avatar with full health bars right from the start. But let's move to the next section and see how this scales into something far more complex. Because while we fixed our game, real-world enterprise code is way less forgiving. Scene 3. The bank account nightmare. Let's pivot from game mechanics to a high-stakes real-world banking scenario. Imagine opening a bank account and Java defaults your name to null. If any system process calls a method on your account to print a statement, boom, a null pointer exception triggers and the entire banking system goes down. To prevent this, you might try to outsmart the system by hard-coding a fallback placeholder right into the variable declaration, something obnoxious like unnamed lazy user penalty. Seems like a clever way to catch empty data, right? Well, let's take a look at what that actually does in the machine's memory. Here is the hidden inefficiency that so many developers completely ignore. I call it the setter trap. First, you create the account. For a split second in RAM, your brand new, highly valued customer is officially registered in memory as a penalized lazy loser. Then, you immediately call a setter to fix it to their real name, like Arav. Yikes. You literally just force the computer to write to memory twice simply to create one single person. That's exactly like naming a baby do not want at birth, filling out the official birth certificate, and then legally changing it to Arav 5 seconds later. It's just a massive, unnecessary waste of computational resources. Scene 4. Constructor overloading to rescue. So what's the solution to this memory-wasting disaster? Constructor overloading. Think of this as providing an express VIP lane for your data. We're offering dual paths for object creation. Path A is our old no-argument constructor. If a user is lazy and leaves the form blank, they go down Path A, straight into the dumpster fire and get slapped with that penalized fallback name. But Path B, that's where the magic happens. By using a parameterized constructor, the user is instantly granted the VIP golden card treatment. The really crucial point here is that, just like method overloading, Java allows you to have multiple constructors within the exact same class. We can offer one no-argument constructor for the lazy path and one parameterized constructor that takes a name and an amount. If they fill out the form properly, they hit that second constructor. They are born into memory with their real name and their real balance instantly applied. Zero wasted memory writes, just pure optimized efficiency.
Scene 5, the disappearing safety debt.
But beware, because fixing that inefficiency introduces the ultimate trapdoor. This is a trap that consistently ruins computer science students on their final exams, and honestly, even catches senior devs off guard sometimes. You might suddenly find yourself staring at your screen, asking the compiler, wait, where did the default constructor go?
Take this innocent-seeming piece of code. You've learned your lesson, right? So you write a nice, clean, parameterized constructor. It looks pro, it looks efficient, but actually, scratch that. It is secretly hiding a fatal flaw.
Because over in your main method, someone inevitably tries to call a new bank account without passing any arguments. And kaboom, you get a massive red compilation error. The program flat out refuses to run. Why? Because Java's built-in hidden default constructor, the nanny that gives you those zeros and nulls, is incredibly shy. The exact microsecond you write any custom constructor of your own, Java assumes you want total control, and its hidden default constructor vanishes into thin air. It's just gone. If you try to use it without explicitly writing it back in yourself, the compiler will drop you right down a trapdoor.
So let's quickly recap the core survival rules from this explainer, because this is absolutely what you need to commit to memory. First, Java's hidden default constructor is a shy ghost. Second, the moment you write a custom parameterized constructor, that ghost vanishes completely. And third, if you still want the ability to create objects without passing arguments, maybe for frameworks or specific fallbacks, you must explicitly write your own no-argument constructor back into the code. You have to be the one in charge.
Which brings us to our final question. Now that you've seen how Java's so-called safe defaults can essentially spawn a corpse, and how relying on setters can absolutely trash your memory bandwidth, will you take explicit control of your memory allocation, or will you keep rolling the dice and let Java spawn you dead? Take these lessons back to your code editor, stay sharp, and always know exactly what is happening under the hood when you create a new object. Thanks for joining me on this explainer, and keep coding.